So this is outline of what I'm going to talk about. And let me first define how we define MSW effect. This is flavor, adiabatic transformations of neutrinos in matter with varying density, driven by change of mixing in the course of propagation, so mixing in matter. And strong transitions occur when neutrinos cross the resonance layer. So what I will talk on developments of main notions and concepts, and I divide my talk in three parts. First is the Wolfenstein paper and some follow-up. This is this period, early one. And then what we did during these 2 years, essentially, and future developments from 95 to 96, and I believe that soon after Morion, 86, all the basics of MSW have been accomplished, and of course there were different developments later. So the Wolfenstein phase, it's amazing that Lincoln was 55 years old when he produced his the most important papers in his scientific life, which is very rare for theoretician. So shortly motivation, it's interesting that he had a paper some years before his 78 one, when he discussed completely off-diagonal neutral currents. That was epoch of neutral currents. Everybody was interested in this, and he has this funny idea that even massless neutrinos can have these off-diagonal currents, and that can produce some interesting effects. Also, amazingly, that he refers to paper by Mann and Primakov, and they discussed a long baseline experiment in our terms with a distance something like more than 1,000 kilometers from Fermilab to Quebec. And Lincoln was very much excited because his ideas could be tested in this experiment. So the key statement is that coherent forward scattering of neutrinos must be taken into account when considering oscillations in matter. So this is the key point. Already for this, he should be merited and he should have a credit in his life and his achievements. He used a generation of K mesons and also optics, and it's not surprising because Wolfenstein was an expert in K meson physics. So what he did, without any derivation actually, he said, okay, what happens that neutrinos acquire refraction index in the medium, and this is the standard expression, where n is the number of scatterers, this is the amplitude of forward scattering, k as neutrino momentum, and that produces some additional phase. And oscillations is phase effect. So if you have some source of the phase or phase difference, this means that you will have some influence onto oscillations. So this is the common exponential factor, is the refraction index. And in general, you have the phase difference, which is described by this expression. This is the difference of refraction indices of two components of neutrinos. Then this is momentum and x. And this is immediately comes from this expression. And then he did explicit computations of this delta f, phase difference of the amplitudes. And he got this expression. I'm sorry, it's written here in below. So what is important here, Fermi coupling constant, number of scatterers, so essentially the G Fermi n. And this is the factor which characterizes his off-diagonal neutral currents. Now, he introduced effective oscillation lengths, which is what we call now refraction lengths. And this is the lengths over which the phase acquired of the order of 2 pi. And so this is expression for refraction length is 2 pi. This is k and the difference of refraction indices. And in the case of massless neutrinos, he was interested. It is this quantity which determines the oscillation lengths. So he made the first estimation, and that was 10 to the 9 centimeters, which is comparable with the radius of the Earth. And this was somehow in the range which is, could be tested in this Primakov-Mann experiment. So it's comparable with the radius of the Earth. Now the refraction length, and he immediately gets this expression, is 1 over G Fermi over n, and it doesn't depend on energy. So that's kind of very important consequence. Now he introduced the notion of eigenstates for propagation in matter, which is an important notion in this business. And these are the states which diagonalize these neutral current interactions of diagonal. And these are the states which have definite refraction indices. These states differ from what we call flavor states, electron and muon, neutrinos which are produced in charge current processes. So that's the origin of mixing in this scheme. And then elaboration of oscillation physics is very simple. So he writes this expression for neutrino state, produced neutrino state, as the combination of eigenstates and matter. And then he immediately gets oscillation formula with this oscillation length equals to L0. Now he has a footnote in his paper when he says that I'm embedded to Dr. Daniel Willer, and he was a postdoc at that time with Wolfenstein, for pointing out the importance of the charge current term, and this is this diagram. Nu is scattering on electrons due to charge current. And therefore, if oscillations involve electron-neutrino, one should take into account the effect of this diagram, which is actually reduced to neutral currents if you do first transformation. It's just electron-neutrino scattering on electron. And there are two important consequences of this diagram. It changes the mixing. It changes the mixing he discussed before. And it changes oscillation lengths also. And in general, it modifies the oscillations in vacuum, even if neutral currents are diagonal and symmetric. So actually, this is what is the most important, what we are using. Now, and Wolfenstein has the second small part of his paper. He was really keen to discuss these massless neutrino oscillations. And I have some comment on this if I can elaborate more. Now, if neutrinos are massive, then there is another source of phase or phase difference, is the difference of masses present. So there's another exponential factor, and therefore in medium you have two different sources of phase difference. And to reconcile them, you need to go to differential equation, and without any derivation, without discussion, he just gives this equation of evolution, equation of motion, which includes both refraction effect, you see it here and here and here, and the just usual mass effect. He derived this in mass basis. And actually, it is wrong that he didn't derive this in flavor basis. In a follow-up paper, he did this, and this is actually in proceedings. And interestingly, is that not only he derived this standard, what we call master formula for neutrino oscillations, which everybody is using to derive results, he also made some discussion applications, for instance, for atmospheric neutrinos. He also mentioned that that the effect which he is discussing, the matter effect, is analogies of phenomenon of optical birefringency. And this is important because I made some other comment. He thanks also another person, and I'm kind of wondering what was this person was saying, who was working on this stuff. Now, Wolfenstein has unknown paper in which he essentially started to talk about adiabaticity. So Wolfenstein has derived formula for mixing angle. This is for tangent to theta, and also for oscillation length. And immediately you can write this just usual formula for neutrino oscillations for two neutrinos in terms of effective mixing angle and the phase factor. This is standard formula. He discusses three cases when L nu, oscillation in vacuum, is much smaller than refraction length. This is essentially nearly vacuum regime. Then if oscillation in vacuum is much bigger than L0, this is matter dominance regime. And in this case, the oscillations are strongly suppressed because of smallness of the mixing, and oscillation length is comparable with refraction length. He also mentioned this intermediate case when he is saying that quantitative results in matter are quite different from that in vacuum. Interestingly, that he is not elaborating on this, the most interesting case. He has a table in his paper, and one can actually find in one of the graphs the effect for small mixing. And clearly, there is enhancement of probability. This is in matter, and this is in vacuum. Again, no further comments, no further discussion of the consequences. He made also another interesting comment in his first paper. This is what we call now vacuum mimicking effect. And he says that independent on value of ratio of oscillation lengths in vacuum and refraction lengths, as far as the phase is small, the effect is just reduced to vacuum oscillation case. Now he discusses some applications, this of what we call now long baseline experiment. As far as solar neutrino are concerned, again, he just pick up the case when oscillations are suppressed. He's saying that if L nu in vacuum is larger than oscillation lengths, refraction lengths, then oscillations are suppressed. And there is no significant oscillations inside the sun. Now he also discusses supernova neutrino in the next publication, and there were some discussions of vacuum oscillation effects inside the supernova. He's saying no, because of strong suppression of mixing, there is no effects here. Now there are a few comments. In fact, refraction of neutrinos has been introduced before Wolfenstein, and in particular in this paper, to detect relic neutrinos using this refraction effect. And refraction index has been computed. Wolfenstein asks Zavattini, and thanks Zavattini for asking the right question. And again, he was working, Zavattini, on birefrequency. And I asked Daniel Wheeler, saying, do you know what really he asked? Maybe he asked immediately on this matter effect, so maybe originally something comes from this question. Unfortunately, Daniel was saying that he doesn't remember well, and Wolfenstein kind of was secretly working person, not discussing much with him, other things. And of course, it's amazing why he didn't discuss and elaborated the case, the most interesting one. Now, I want to skip this, and there are these stars, if you ask me then. This is some initial discussion of follow-up, and this is about the paper by Barger et al. In this paper, you can find the following statement. There is always some energy where you have this relation between vacuum, oscillation length, refraction, and mixing angle. And hence, theta mixing angle in matter becomes 45 degrees, either for neutrinos and antineutrinos, depending on sign of delta m square. And they give this dependence of this mixing angle in matter on the energy of neutrinos. And this is the oscillation length in this peak. It doesn't look like resonance. They are not saying about resonance, and didn't actually explore the nature of this effect. So this is also some figures from this paper, and you see again enhancement of oscillations in some range of energies. So this is second part. This is some background. I can elaborate more, but what is important that Mikheyev, so we were in the same department in Institute for Nuclear Research of Academy of Sciences, and Mikheyev was experimentalist working on Buxton telescope, and in particular on analysis of atmospheric neutrino data and searches for oscillations in atmospheric neutrinos. Now, I myself was very much interested in oscillations, and actually in the early days elaborated this graphic picture which I used to understand what's going on. The effect was understood using this picture, which actually differs from what we are using now, because this is in terms of amplitudes, not probabilities as we are using now, and not in analogy with spin precession in magnetic field. Nevertheless, this gives correct results once we have motion in one plane. This is a real part of electron neutrino probability amplitude, and this is real part of muon neutrino amplitude. So in this case, oscillation is just precession around this mass state axis, and periodic change of projection on this axis gives the amplitude to find electron neutrinos. So the starting point of our collaboration was this question sometime in the spring of '84. And Stas asked me, do you know about the Wolfenstein paper? Is it correct? And should we take into account his effect in an oscillation analysis of atmospheric neutrinos? I didn't know about Wolfenstein paper. I started to read it. And the first what I did, I just took his formula, dependence of sine squared to theta m on this L nu over L0. And the result was astonishing. This is what I got. This is from original drawing. So that time I haven't even seen a Barger paper. But for small mixing, I have found that you have this maximal mixing effect, and this is the condition for this maximal. And I said, oh, this is the resonance. That's really like a resonance. And this mixing becomes, at this point, effective mixing in matter 1. So what we did, actually, what people didn't do before us, we started to understand if this is really a physical phenomenon, what's the physics behind this resonance. And in fact, in the resonance for small mixing, we have this equality of L nu and L0, which means that eigenfrequency of the system coincides with eigenfrequency of external medium. And when you have this coincidence of eigenfrequencies, you have this resonance phenomenon. Actually, there are many other features of this resonance which actually fit the standard resonance. The width of the resonance is proportional to sine to theta, the smaller angle, the narrower the resonance, and this is the length of resonance, the length of oscillation in resonance. Now, already in the first paper, we realized that there are two different consequences of this resonance and realization, if you want. One is the case of constant density, a continuous spectrum of neutrinos. And in this case, you expect this enhancement of oscillations at some energy, certain energy. This is actually what also Barger mentioned. Another one is when you have varying density and monoenergetic neutrinos, and that led us to this adiabatic conversion of neutrinos, which I will discuss now. So this is, again, comments which, if you want, this attempts to understand why people didn't do this before. Now, if you have varying density case and monoenergetic neutrinos, then these neutrinos at some distance cross this resonance layer when you have when resonance condition is satisfied, and there is some resonance density which is obtained from resonance condition, and the width of the resonance is proportional to tangent to theta. Now, if resonance layer is thick enough so that at least one oscillation length can be obtained inside this resonance layer, then you expect strong effect. Essentially, this is what is then recycled to adiabaticity condition. So this is the size of resonance layer. It is proportional to delta rho, which is given here, and the gradient of density. So actually, we also mentioned that one should be careful of using some of these parameters obtained in the case of constant density case. It was some confusion, actually, one of the problems which we tried to understand. So suppose you have medium with varying density, and at some layer you have these resonance conditions when you have resonance. Now, you can imagine that, so suppose the first effect, oscillation effect, is very small, then your system enters this resonance layer, and then strong oscillations develop, and then there is no oscillations after that. This is in the spirit of Rosen and Gell paper. This is slab model. And we understood already that this model is actually wrong. And the simple question is, okay, then the effect from here and at the end should depend on the phase which is acquired in this layer. And why we should have strong transition, why the phase is like this, and then we will get something like what we have in the beginning. So actually, in the first drawing, I had this picture for conversion in the case of varying density. So there's a strong transition in some range. Here in this range, the width of resonance layer becomes too small, and here there is no resonance condition at all. So that was first drawing, but then the question is, why not like this? Why picture is not like this? And then the phase depends on how thick is your resonance layer. So we did numeric computations which support this picture. How much I have? Okay. Okay, so what we did, we used Wolfenstein equation and derived these equations for probabilities. Now, P is the probability to find electron neutrino, and R and I are real and imaginary part of this element. Essentially, this is what we call now elements of matrix, density matrix, or components of neutrino polarization vector. So we have derived this equation and then just make numerical computations, and many results have been obtained by these numerical computations. But the understanding, again, for understanding of the results, I've used this graphic representation, which I have elaborated several years before. So what's going on, you have this electron neutrino axis, this is muon neutrino axis, and when density changes, then this axis of eigenstates moves, right? So suppose you have in the beginning pi over 2 mixing angle, then going to lower density, this vector changes and ends up here. This is nu2. It coincides with the axis which corresponds to nu2 mass eigenstate. So in general, if initial mixing is not small, then you have this precession, and then what's going on? The axis is going, if it is going slowly, then it actually pulls the neutrino vector which precesses around the axis. So that was our understanding, and that's we got our results. Actually, this one allows immediately to get this sine squared to theta famous factor. Now, Wolfenstein later, we have sent one of preliminary versions of our paper to Lincoln, and then we got a short letter from him some months ago, and in this letter he has written that it should be no strong transition inside the sun due to adiabaticity. And then he gave the reference to this paper, to which practically nobody refers and nobody knows. This is in proceedings. He even didn't give the talk. It was just a contribution to this conference. Although some probably sitting in the hall were at this conference.
It is cited in the PDG.
Maybe, yeah, but.
No, it's not maybe. It is cited.
Good, yeah, good. I'm citing this. So we couldn't find at the time this paper. But what we started to do, we referred to this kind of pooling effect like adiabaticity effect. And the condition for strong transition of width of the resonance layer we call the adiabaticity condition. And our reply to Lincoln was that it is due to adiabaticity. We think that strong transitions can occur. If you want, I have some comments which I think why Wolfenstein thought of in this way. So these are comments I can go. So we generalized our adiabaticity condition and introduced adiabatic factor in the form which actually we are using now, essentially. Now, this is adiabatic conversion. So if neutrinos are propagating from very high density to lower density and meet resonance somewhere, then your final probability is given by this sine squared to theta. And this is obtained just precisely from this figure. And you see here the density changes, then the eigen states nu2m, which coincides with electron neutrino in the beginning, pulls down the vector and ends up in this way, and this is mixing angle in vacuum, and so the projection is sine theta, and therefore probability is sine squared to theta. This is how the result has been obtained. And then we also made the computations which confirm this. So this is a general case. So in the next paper, we elaborated the theory of adiabatic conversion, which is kind of not well known. And the fact of this paper was that it was first rejected, then resubmitted, and we had these results already by the end of the summer of 1985. Eventually, it was published. And the way we have elaborated the adiabaticity condition, we actually derived the equation of the third order in P using the system of three equations, and then adiabaticity corresponds that we actually neglect these high derivative terms and then got a final probability which just exactly coincides with what we are using now for adiabatic solution. And this is how the probability depends on distance, depending on where neutrinos are produced. If neutrinos are produced not far from resonance, that we have still some significant oscillatory picture. The further neutrinos from resonance neutrinos are produced, the smaller the oscillation depths here. And if neutrinos are produced very far from resonance, then it just has this non-oscillatory transition. Now, what is this Wolfenstein unknown paper from this 78? What's interesting that, in fact, he discusses adiabatic conversion for massless neutrinos, and he obtains the formula, which is nothing but adiabatic formula which we are using now. So this is some comments on publications. Again, if you ask, I can reply. And then the third part is our further developments. And one of the things is presentation of MSW as a level crossing phenomenon. And this is very well-known paper by Hans Bethe, and he has derived the dependence of eigenvalues on the density of neutrinos, and you see here 2 levels. And then if adiabaticity is fulfilled, then neutrinos are moving along this one curve here, and so it starts from electron neutrino and end up to muon neutrinos. So in the case of adiabaticity, there is no transitions between this level. And this has actually very important consequences for further developments. Well, I should say that even before Hans Bethe, this picture has been drawn by Nicola Kabiba, and it was during the Wien conference in '85. And well, I discussed this with Sergei, and he told this to Nicola, and Nicola came to me during excursion and showed me precisely this picture with level crossing phenomena, asking, do you agree that this is correct description of your effect? And I said, yes, I agree. And I said this not because I was too clever, but because I knew this from Valery Rubakov, who told me in the spring of this '85. He's saying that your phenomenon is kind of similar to what's going on when monopole is coming and approaching the proton, and then you may have transition of proton to decay of the proton induced. So he explained me at that time what's going on. So essentially, almost this level crossing paper has been obtained again in Barger et al. Early, and these are nothing but level crossing schemes, but they didn't elaborate, they didn't. And the point is that also they used energy scale here, not the density. Now, this is something really amazing, and I think this that should be actually given credit to Albert Messier, who actually had the paper in this Morion workshop, and I think many people were at this workshop. So the bottom line, he really elaborated the theory of adiabatic conversion and even adiabaticity violation in very strange form. And even I was sitting in the hall, I couldn't understand essentially what he was saying, because till the end he used this quantum mechanical operator description, and simple things he's just discussed in terms of operators and how operators are transformed. Nobody understood. Later, I just studied this paper, put this in kind of reasonable terms, and what I have realized that this equation, which you can find in his paper, is just reduced to this equation for evolution of eigenstates in matter, which is the key for this adiabatic theory or adiabaticity violation. So just this guy should go to sigma 3, this guy should go to sigma 2, this is sigma 3. This is just wave function for neutrino eigenstate. So he introduced adiabaticity parameter in our kind of way, which we are using now. And so he found even this formula, which we call now Park formula, with this beta square, which is jump probability or flop probability. And I'm almost done. But I want to still apprise the organizer, so just keep patience for one slide more. So, so Haxton and Park start to use some analytic expressions for this jump probability when you have adiabaticity violation, and they suggested to use this Landau-Zenner, which is valid for linear density change. So essentially, this beta square parameter introduced by Messier, they use this expression, and gamma is precisely adiabatic parameter, which has been introduced even before. Haxton used some limiting cases, and Stephen has introduced a general formula with this jump probability and non-zero theta. And this is final kind of slide. This actually the first paper which I saw, this graphic representation of which we are using now. So they have in this paper Michel, Daniel, and Jim Rich also.
The credit for this is Jacques Boucher.
Okay, good. So very good. So this is in a way analogy of spin precession in the magnetic field, and this is how transition occurs. This is in terms of the probability. So what we use this P. So they use P. P, R, and I. This is what's in our paper. They just use another notations, but it is essentially the same. So I'm almost finished, and there are further developments in various directions. You can ask me, what is this? And this is the summary of merit of Wolfenstein. This is what we did, and these are further developments. And I want to finish by this. So in 98, in the final Homestake publication, there is no reference to MSW effect, and they just refer to magnetic field and precession of magnetic moment in the solar magnetic field. So in 2002 and 4, LMA MSW has been established as the solution of the solar neutrino problem. In 2008, Kabiba said that the MSW is spurious solution, and actually the data support just original Pontecorvo idea for no reasons. In 15, in scientific background description of Nobel Committee, they put formula for oscillations in medium with constant density concerning the sun and the solar neutrinos. In 17, Boroxina further confirmed LMA solution. So this year I asked London, he said, no, Homestake never seen time variations of the signal. Thank you.
Thank you very much. Question, comments? Sergey.
You showed the slide with the Landau-Zener expression. This expression for the large mixing angle, sine squared theta 1, 2, gives a very bad expression, value for the probability. So it doesn't work really. So, I told you that I'm going to discuss only something which is, say, up to the first part of 86. And there are many developments, of course, and for instance, here, so it's written that adiabaticity violation and the formalism has been elaborated, and exact solutions have been obtained for different density distributions. And yes, I agree with you, and probably one of the most precise results in the case of adiabaticity violation for large mixing has been derived in your formula in 87 or 88, right? Something like this. But it's interesting that nature actually, it looks like realizes this really adiabatic well, good adiabatic solutions everywhere.
I would like to point out that Carl Albright was sitting behind me, and we collaborated with Lincoln for a couple of years at CERN. I really want to honor his memory. And I always thought he was a magician. He was not a physicist, he was a magician, because you see, he said to me explicitly, I can never get any phases right, I can never get factors of 2s and i's, but he always got the results correctly.
Well, his potential was, has a wrong sign, as we know, and a factor of 2 missed.
That testifies that it was his own work, Professor Lipari.
Calculations for the atmosphere, because in that case you really had to integrate numerically the propagation equation.
This is what he did. Actually, I was immediately switched to this varying density because I was more fascinating by this. Okay, for constant density is it's simple, trivial, and it's essentially introduced in Wolfenstein. I just said, yes, it's correct, I think, this paper, and then they proceeded with the numerical computations without me.
So in some sense, also the sun could be obtained just numerically.
Yeah, sure. Yeah, of course.
Other questions? Please.
Maury Goodman, Argonne. I'd like to hear your comment about publications.
Okay. Yeah. Well, Well, I have written many things because that's kind of, you can read this later just to have a better understanding of what's going on. So we submitted the first paper in 1984 and to Physics Letters B, and it was rejected. No reason for quick publications. Though we updated our paper and then submitted it to Ядерная физика, which is Soviet Journal of Nuclear Physics. And so in the spring of 85, it was almost, it got a negative report, and it was almost like rejected. And so I also heard that Bruno Pontecorvo was kind of skeptical to this idea. So then Zatsepin, just seeing how we are kind of struggling, he took our paper to Italy, and so he was collaborating with Castagnoli, who was editor of Nuovo Cimento, and they have LSD results. So they are in both LSD collaboration, so they were in the same collaboration. And Zatsepin told us, okay, let me help you. I'll take this paper and ask Castagnoli to consider it. And he said, okay, maybe this is wrong. And this is what he said to Castagnoli. We don't know. Maybe it's wrong, but soon people will forget this. But if it is correct, then it's important result. So why not to publish? It happens very soon. But then, surprisingly, the paper was accepted also to nuclear physics. Although they kind of close. Paper are nearly the same, but with some difference. For instance, in one we discussed three-neutrino oscillation conversion case. And so I heard that Kobzarev, who was an editor of nuclear physics, actually took more careful look at this paper. And then the next, so the first presentation was in Savonlinna, and Cecilia was here. And actually, even I asked her, so can you mention this or something like that? Who was brave was, oh my God. I have even photo, you by the way, and also, let me finish and then I will show this photo. So, Conforto, yeah. So he was organizing parallel session, and they give me 15 minutes in the end of the session to present these results. So we submitted our JET letter, second paper to JET letter with adiabatic solution in, I think it was September of 85, and was again rejected. Again, no need for quick publications, and then we submitted it to JET, and it was published next year. And then most of our results have been presented at Morion workshop in Teen, and so that is actually what was our independent to anything accomplishment. And but I want to kind of to say another thing. So that was the time of perestroika, and it was completely stupid decision that before we can send paper abroad, we need to publish it in Soviet journal. And publication in Soviet journal may take a year or so. So what we decided to publish paper in proceedings of the conferences, and then summarize everything in a review. And so we had this review in journal Uspekhi, which actually kind of summarize of our contributions to different conferences.
Michel Tribier.
Yes, Michel Tribier. No, I just want to add a curious point. When you presented your paper in Finland, we had it by one of our colleagues which were present there. Unfortunately, there was only half of the page which were copied, so it was difficult. Nevertheless, we tried to understand and compute, and it was just at the time where the GALEX collaboration was starting to be funded, and we very well remember that as a member of GALEX, we presented at a meeting of the collaboration to Till this idea that you have proposed of a MSW solution to the solar neutrino problem, and Till was absolutely, it was a disaster for him, because at that time he was trying to have enough funding to buy 30 tons of gallium with a simple argument that it was impossible to explain the result of the GALEX experiment. He can explain it in just one word. And unfortunately, this, for him, at that time, seemed a very complicated solution, and it was a disaster. Soon after, we realized that it was very good, but the first reaction was not so good.
So
I have a small comment. I've talked to you about this before. So, Stas told me the story one time that the way this got started was when he was doing some numerical calculations and he was getting crazy results because he was doing the numerical stepping and he'd hit the resonance or whatever by accident. And he came to talk to you, and it was you that then straightened it all out. But the nice thing, if it's correct, is that this got started in some way by a numerical problem that was run into in the spirit of our mistakes leading to good things.
That was a total political thing. I had nothing to do with the importance of MSW.
Yeah, Sergey.
Concerning the 7 linear meeting, I mean, you tend to forget that actually I was present when you were asking time from Cecilia Arskog and Gianni Conforto, and they both refused. And then you came to me, and you asked me to present your work at the plenary talk I had. And I told you that I have to read it, and then I will decide. Now, meanwhile, you got time to speak, but you didn't inform me about that. So I devoted 15 minutes of my 45 plenary talk to the description of your paper. And I think that Kabibo, who was present at my talk, who got it immediately. Actually, I think that I understood about 75–80% of what you did at that time. So this is how it went. I think that the first plenary presentation of your paper at an international conference was done by me.
Cecilia.
I would like to say that also you had very strong competition in that conference because John Simpson was there and talked for the first time about his 17 keV neutrino. Yeah. So, and I also, I mean, admit that I didn't understand what you were talking about. So that's.
Yeah. So I think that we can close here. Thanks everybody. Now, before you get your coffee, you have to make some work. You have to, first work is to